Hello, Math 410 class. Today we're going to be covering Unit 3.1, at least just the first part of it in this video. The later parts of this section, it's pretty long, so those will be in different videos. First thing we're going to do is, I would expect you to read all of this sort of lead up here and the introduction. To put it in a nutshell, we're going to be looking at what are known as second order linear differential equations with constant coefficients. And so what that means is that the coefficient of y double prime, which we're going to call p, y prime, which we're going to call q, and the coefficient of y, which we're going to call r, those have to be just numbers, okay? The right-hand side, this can be a continuous function of the independent variable, which in this problem is t. You'll also see x as an independent variable later on. Now, if you just get 0 over here, so if g of t is just straight up 0, then you get what's known as a homogeneous differential equation. And so those are going to be what we're studying in this section. Eventually, in Unit 3-2, we'll get into non-homogeneous equations, where you actually get like a function of t over here. And so if you get something that's not 0, even if it's just like a number over here, that's called non-homogeneous. Okay. We'll get into linear independence as we need it. Its meaning is somewhat similar, almost identical to that of linear algebra, but if you don't know what that is, it's not really important right now. Okay, so let's first talk about what the general solution of a homogeneous differential equation, second order with constant coefficients, should look like. Well, let's go back to the one-dimensional case. So let's suppose we had y prime equals k times y. Well, really, I mean, the solution to this is just an exponential function, right? Which function, when you take its derivative, equals a constant times itself? Well, that's, of course, exactly e to the kt. Or you could even put a c here, a c e to the kt. The point is that the derivative looks an awful lot like the original starting function. And it turns out that that's actually not different for second order linear equations with constant coefficients. So the answer here is like which family of functions have sums of derivatives that add up to 0? Well, that's also exponential functions. Now you might be thinking, like, is there an example? Well, sure. I mean, just to go really easy, what if a and c were both 1, x of t was e to the t, and b was -2, right? Then all derivatives are just e to the t, and so you'd get 1 e to the t minus 2 e to the t plus 1 e to the t. Well, that's dead on equal to 0, right? So something like this certainly would be an answer for that problem. And finally, there is actually one other class of functions that has this property. That would be actually trig functions. Think about it. What if x of t were, I don't know, how about cosine t? And a and b were equal, a and c were equal, let's just say 1, and b was 0. Then the second derivative of cosine t is negative cos t. So you'd have negative cos t plus 1 cos t. Well, that's dead on equal to 0 as well. But for those of you, well, actually, we've all seen it by now, that trig functions are really just sort of a complex exponential, right? So really this does sort of capture all possibilities, but we'll get into trig functions in a later video as they sort of show up when complex numbers are involved. All right, so moving on, let's remember the spring equation. This is what's known as a spring mass equation. And let's suppose our coefficients, so let's say m was 1, b is 10, and k is equal to 9. And what each of those numbers, m, b, and k, what they represent is given right here. Okay, so what we get is this differential equation, that x double prime plus 10x prime plus 9x equals 0. And now we're going to make a guess, or an ansatz, as to the solution, and we said that exponential functions should solve this. So let's see what we get. Well, the first thing we need to do is actually compute, well, if x is e to the rt, then x prime is r e to the rt. And you guys might have done this on a previous homework. Okay. Then plugging everything in, what we're going to get is that x prime prime plus 10x prime plus 9x, well, that's equal to, we'll just plug everything in here. You get r squared e to the rt plus 10r e to the rt plus 9 e to the rt, and that has to equal 0. You can factor out e to the rt, and you get r squared plus 10r plus 9. And e to any number is never, ever, ever 0, so that what that implies is that we get this, what's known as a characteristic equation, that r squared plus 10r plus 9 has to equal 0. And you can solve this. The solutions are, of course, minus 9 and minus 1, but we'll get to that in a minute. Let's first just leave that where it is. But now let's, so what I want to connect this to the last thing we did in Unit 2, and that is to find the characteristic equation by first converting this to a linear system of equations. So if we remember how this goes, we put x1 equal to x, then if I'm not mistaken, we put x2 equal to x prime, and so that makes that x1 prime, right? Then let's see what else. X double prime, well, going back up to the equation here, x double prime, well, why don't I solve this? This is minus 10x prime minus 9x. Oh, well, x double prime is really just x2 prime, right? Because x double prime would be x2 prime. And now x prime is x2, and x is just x1, right? And so we get a system of equations now where x1 prime equals x2, and x2 prime equals minus 9x1 minus 10x2, right? And this can now be converted into a linear system, so something like this. X1 prime, x2 prime equals the matrix 0, 1, minus 9, minus 10, x1, x2, right? And now to find the characteristic equation, what we need is we need the determinant of, let's see, this matrix, but then minus r times the identity. So you get like minus r, 1, minus 9, minus 10, minus r. And that works out to be and if that doesn't look familiar, right, there it is right there, you see that the eigenvalues would be r equals minus 9 and r equals minus 1. And those are actually the same as the so-called characteristic equation from part A up here. And so if you work all this out, I'm not going to do it, but I encourage you to. If you follow the old method from Unit 2, what you'll find is that the top row of your answer, so x1, which is also known as x, the function we're looking for, will be given by c1 e to the minus t plus c2 e to the minus 9t. And in fact, we can sort of shortcut all of this stuff here and instead just run straight to this characteristic equation right here. And you'll notice that it factors. And these numbers show up exactly here. And as long as they're not repeated, so minus 1 and minus 9 are definitely different, since they're not repeated, it's just c1 e to the first 0 times t plus c2 e to the, and then second 0 times t, where 0 refers to the 0 of the characteristic equation. And so that leads us to this remark here that in part A, I was already calling it the characteristic equation or the characteristic polynomial, but it actually has the same name as the previous stuff we've done in Unit 2. and for the same reason, and hopefully the connection is clear. All right, so now let's talk about what happens when we have real distinct roots. So this first one here, let's see if we can run straight to the characteristic equation. Well, this is y double prime, this is 3y prime, and this is 2y. So I think the characteristic equation is going to be r squared plus 3r plus 2 equals 0, if I'm not mistaken. And now I can factor this as r plus 1, r plus 2 equals 0, which says r equals minus 1, r equals minus 2. Okay. And now what that tells me is that, let's see, y here is going to be c1 e to the minus t, notice t is our independent variable, plus c2 e to the minus 2t, right? So I'm just taking these numbers, multiplying them by t, and those are the powers of e. All right, now to solve with my initial conditions here, so we're going to find what's known as a specific solution. What we need is, it looks like we're going to need y prime. So I can find y prime really quickly. That's minus c1 e to the minus t minus 2 c2 e to the minus 2t. Just taking the derivative. Nothing crazy going on there. And now plugging in our initial data. So when t is 0, I'm supposed to get an output of 2. So 2 is what I get when I plug 0 into y. So I get c1 plus c2, I think. And furthermore, minus 1 is what I get when I plug 0 into y prime. So I get minus c1 minus 2c2. And now solving this, if I add downwards, I get 1 equals minus c2, which says c2 is equal to negative 1, which says c1 is equal to 3. And so just plug everything back in now. Well, I get y equals 3 e to the minus t minus 1 e to the minus 2t. Moving down here. Notice our independent variable is t, so t should be the only thing in our final answer. Go ahead and try this one if you like. Pause the video now that hopefully you have the idea. But we're going to do this together right now. So we get x double prime plus x prime minus 6 equals 0. So I think the corresponding characteristic equation should look like this, which factors as r plus 3, r minus 2. So r is minus 3 and r is 2. And so what that tells me is that x equals c1 e to the minus 3t plus c2 e to the 2t. And you'll notice I also need x prime if I'm going to get a specific solution. So x prime, well, that's minus 3c1 e to the minus 3t plus 2c2 e to the 2t. And 1 is what I get when I plug 0 into x, so c1 plus c2. And 0 is what I get when I plug 0 into x prime, which gives me minus 3c1 plus 2c2. And I'm not going to go through the work of solving this. I'll just give you the answer. C2 is going to be 3/5, and C1 will be 2/5. I encourage you to verify that. I don't think it's too much work. And so what that tells us then is that x equals 2/5 e to the minus 3t plus 3/5 e to the 2t. All right, and now last one. This will be the last problem from the video today. So let's see here. Well, characteristic polynomial, again, pause the video if you want to try it yourself. But characteristic polynomial is going to be 2r squared minus 3r minus 1 equals 0, right? So we take the coefficients, and those are the coefficients of r squared, r to the first, and the constant coefficient. You can't really factor this. What you're going to get, I think, is through the quadratic formula. You're going to get negative b plus or minus the square root of b squared minus 4 times a times c, so you get plus 8 all over 2a, so 4. Well, that is r equals 3 plus or minus root 17 all over 4. Okay, and so what that means is that x will be c1 e to the, and now bear with me here, 3 plus root 17 all over 4 times t plus c2 e to the 3 minus root 17 all over 4 times t. And then I'll help you find x prime here. So x prime is going to be c1 parentheses 3 plus root 17 over 4 e to the, well, 3 plus root 17 over 4t. And similarly for the second term here. All right, so now what you would need to do is fill in 0 equals, well, that's what when you plug in 0 here and you just get c1 plus c2. And 1 is what you get when you plug in 0 to this. So you get c1 3 plus root 17 over 4 plus c2 3 minus root 17 over 4. Okay, I'm not going to solve that for you. I'll just give you the final answer that x equals 2 over root 17 e to the 3 plus root 17 over 4t minus 2 over root 17 e to the 3 minus root 17 all over 4t. So make sure you can solve that. I don't mind if you don't rationalize the denominators here. That's no problem to me. So in the next video, we'll get into what happens when we have repeated real roots. That kind of changes things around a little bit.